Le prof nous entend. On part au temps, qu'est-ce qu'il y a en ce moment? Encore? Mais je sais pas si encore 40. Non, attends, encore une fois. Alors, le DMD, donc crée de ta base. Quoi de non? Sur le truc, genre en mode. Tu dois inventer une nouvelle chose. Ouais, c'est le truc qu'on a fait. Ouais, c'est le même exo. Il faut le refaire. C'est pas la même chose. Non, tu as combien de barres? C'est un deuxième. Tu l'as déjà fait, tu l'as soumis. Sors ton ordi. Non, moi c'est sur mon ordi, j'ai rien. Tu sais, on est fait en. C'est quoi? Non, c'est pas ça. Il fait rentrer, ouais. Vous avez rendu dans les temps? C'est sûr qu'on l'a fait ensemble. Moi j'ai pas vu que ça marche ça. Ouais, c'est lui, il a pas fait du tout. En gros, si tu vas voir maintenant, c'est pas possible. Tu pourras te marcher. Après, il y en a un truc en commun avec mon fils, il y a des mêmes, mais personne. Au début, pour le coup, ça avait bien pas que c'était individuel. Ça va, ça va, ça va. Ouais, bah au départ, ouais, du coup j'avais commencé. Ah oui, c'est vraiment. Tu dis que notre. Non, mais le truc, c'est que si les vélos, nous on prend juste le paris, on a des vélos, avec des vélos, c'est sûr.
Time to do something. What I got for today? Very simple circuit. I got this. Very simple circuit. Simple circuit. Can you tell me what will happen when I turn the switch? Any ideas? silence. Okay. Maybe I'll simplify the task. I have 0, 1 step, 1 coil, and 1 capacitor. Can you write the Kirchhoff voltage law for this circuit? Kirchhoff voltage law. Sum of all voltage drop is 0. Silence.
Sir, you want us to write like U for the resistance and U for the condensator?
Oh, okay. Thanks. What it will be? Resistance multiplied by current. Yes?
Yes.
Plus.
Okay.
What's for coil? Inductance multiplied by first derivative of the coil's current. Yeah?
Yes.
Because it's a self-inductance EMF. Plus capacitor voltage is a sum of all charges flown into capacitor and equals to, it was E0, let it be E0. Kirchhoff's voltage law. Nice. Now I can do one trick with this. The idea is to transform this equation, it is an equation, to the one already solved. To do so, I need to remove integral. How?
As by complex numbers?
At this moment we will do it in time. No, we can use a bit different trick. Let's take a first derivative of this. And also, to make it look like original, divide by inductance. This will give us second derivative of the current plus first derivative of the current plus 1 LC current equals to the first derivative of the EMF. This is uniform differential equation already solved. Trick is what very similar equation describes string oscillation. And it's already solved. That's good. I need to do something with, about transient. And when we speak about transient, my very simple example to understand idea with transients. Let's say I have simple DCA and one capacitor switch to be closed at time 0. This will be ground, second resistance, and here I will take my voltage. Simple schematics. Can we name voltage at the time before 0? What will be voltage before 0? Ideal capacitor, this one is DC source. What's the resistance of ideal capacitor in DC mode? Infinite. Yeah. So there will be no current, and I can guarantee what pre-computation voltage will be. Okay, and what will be voltage at a time infinite? Let's say. What will be voltage at infinite time? Ideas? Resistance of ideal capacitor is infinite. So there will be no current in this branch. The only current will flow here. Yeah? What will be this current? By the Ohm's law, E divided by L1 plus F2 and multiplied by F2. So I can draw this one will be E F2 divided L1 plus F2. This is what it's, let's say, infinity. And what between them? Ideas? All capacitor discharges are the same. This will be a power minus alpha time. Here alpha is 1 divided by CF2. Why I'm drawing this? Actually, it's E1 minus F2 divided by 1 plus F2 a power minus alpha time. Yeah, it should go here. Why I'm drawing this? This is pre-fault regime. This is stable or pre-computation. Okay. I deal with faults, so pre-computation regime or mode, infinite time mode, stable mode after. It's also called enforced mode or enforced regime. Better use mode. And this one, transient combinated exam, is a free mode or free component. Also, no problem. Pre-computation, enforced or infinite time component, and free component. Transient can be, it's easier to analyze transient if you can separate free components from enforced or infinite time or stable components. For our small circuit, to find a free component, I'll need to solve an differential equation. It's a second derivative of free component current plus double alpha first derivative plus omega 0 EF equals to 0. Here, alpha L divided by double L is a decay constant. It's a Decorum constant of decay. And omega 0, wait 1 second, maybe I made a mistake. I needed square here. 1 again. It's an oscillation frequency. For such kind of equation, solution is known and common. And solution will be free current as a function of time, I1, a power will be plus I2 e power to time. What's this? I1 and I2 are constants. Constants depending on pre-computation state or merging constants. Also, you can hear term border conditions. These are dependent on border condition. What was before I turned the switch on? And these ones are roots of equation. I need to solve so-called characteristic equation. It will be lambda square plus 2 alpha lambda plus omega 0 square equals to what? To 0. From which? From here. I will get 2 roots. It's a square equation. Square equation. So, these roots will be minus alpha plus minus square root from alpha square plus omega 0 square. To simplify notation, I will introduce beta being square root from alpha square, should be minus omega square equals to x square divided by 4x square and minus 1 against LC. So, free current component will be a power minus alpha multiplied by I1 a power beta time plus I2 a power should be minus beta time. Yeah, here is a nice formula. For the free component, common current will be free component plus some enforced component or stable mode component. Blah, blah, blah. Nice formula. I will return to my circuit. Circuit. Where is my circuit? So let's say I have some E0, I have nice switch, I have capacitor, I'll have what I need. I will have resistance and coil. Oh, here is my coil, here is my ground, and here will be some current because capacitor will discharge when I turn the switch. Yeah, simple. What is current at the time before zero? There will be any current? No. Zero. Nice zero border condition. That means what in time zero, current is zero, it's clear, and what we will get here? Minus E0. We have an easy way to determine this border conditions. So I2 will be equal to minus and 1 and equal to E0 divided by double beta N. Now our free current will be, it's our free current minus E0 divided by double beta N, yeah, a power minus of a power beta time minus a power minus beta time. Oh, we see something decaying. This means decay. And what about this term? It's unclear. I can write three components of the coil voltage. It will be H EF equals to E0 divided by double beta A power minus alpha multiplied by alpha is beta A power beta minus alpha plus beta A power minus beta. Nice. What uses? This is three component of the coil voltage. 1 second, I will write a free component of the capacitor voltage. Why I'm writing this? 1 second, you'll see. Free component of the capacitor voltage will be E0 divided double beta means of bet power minus bet time. Okay, I wrote. And what? Formula and formula. What's behind? There is two cases. In one, alpha is less than omega 0. Rho is less than double wave resistance. Wave resistance is a square root of L divided by C. In other case, alpha will be bigger than omega 0, meaning what L is bigger than double rho. And what? In this case, what will be better? Square root of alpha squared minus omega 0. Who wanted complex number? Here is your complex number. What does this mean? It's a free, I will use F, oscillation frequency. My network will oscillate freely. Free oscillation will be theoretical resonance frequency multiplied by 1 minus F squared divided by 4 square of the wave resistance. This thing will oscillate, but oscillate not on ideal resonant frequency, but on frequency near. For good coils and good capacitors, difference is very narrow, but it will oscillate. And on a different frequency. For this case, current will be minus 0 divided by omega Fl, F power minus alpha sine omega Ft. What's this? Can you tell what I'm wrote? What's in time? Something? Let me introduce. This white formula is this yellow signal. I have a circuit time. Here I have time or not time, it's not important. In case alpha is less than frequency, process will look like decaying oscillation, like this. Alpha determines this line of decay. And frequency, this frequency is, here it is. I'm changing capacitance, frequency changes. Here it is. For small resistance. For small resistance. And what will be for high resistance? That will be real. And we will see a minus of the decaying line. Now, moment. There is a resistance equals to double square root L divided by C. It's called critical resistance. Take a look. I'm increasing resistance. See what happened? I'm increasing decay. Here it is. It's a critical resistance. If contour resistance is less than double wave, we see a process of decaying oscillation. If I pass over critical resistance, you see an exponential process. Yeah? One moment, I'll do here my oscillation. I will change scale. Multiple. I'm powering network from the pulse generator. It's like hitting the tuning fork. It oscillates on its native resonant frequency. And there is scope bit unhappy. Maybe this will make my scope happy. Here, red line is a result of Fourier transform. Yellow line is a voltage of capacitor in time. Red line is a result of Fourier transform. It widens. Yeah. Oh, Fourier transform. Maybe like this. Hey, come back. What do we see? Spectrum of a periodic of sequence of a periodic signal. Yeah? Takes a wide range of frequencies. Actually, it's a set. But we can look at the set at a discrete frequency function. High resistance. Now, I'm decreasing resistance. Why spectrum widens? What happens with the spectrum? I'm decreasing resistance. Why it widens? Because these pulses are very narrow. and instantly. Whoa. What is this? Aperiodic signal. Wide spectrum. Yeah? You see? Set of aperiodic signals and wide spectrum. Resonance circuit. What kind of spectrum do we see? What shall it be at the end? If resistance would be zero, superconducting circuit, what will be at the end? Aperiodic wide spectrum. Periodic narrow. What will be for ideal? Aperiod, it's a sequence of aperiodic signal, kind of spectrum. And this one. Over the loop, over the loop. I will left only one. What happens? Any idea? For a periodic network, we see a wide spectrum. Actually, it's a sequence of pulse. So for sequence of pulse, we see a spectral function of the pulse repeated on the set of discrete frequencies. We see very wide spectrum. At the moment when network becomes resonant, what happens? All energy now concentrates on the one frequency. It's this one, free oscillation frequency. It's another view on a resonance. When network is non-periodic, all energy is spread on the wide frequency range. And on every particular frequency, energy density is quite low. When network becomes resonant, all energy concentrates on one particular frequency, omega f. And we remember previous we saw this 16 volts from nothing, from half a volt. It's what happened. Here we have a concentrated energy. Energy amount is the same. What generating supplies, all pulses are equal. Generating supplies same amount of energy on each pulse. But here, when resistance is low, when dissipation is low, energy concentrates on the free oscillation frequency. When dissipation is high, Here it is, white spectrum. Energy is spread like butter on the wide frequency range. That so-called decrement or decay factor of the contour is divided by rho or is divided by square root of LC characterize energy losses in the contour. It's not very often used. Often used is a quality 1 against by decrement. This Q quality parameter is a voltage in resonance divided by voltage in non-resonance. What we saw, 16 volts in resonance and half a volt in non-resonance. 42 will be the Q. It's an amplitude of resonant current. We can analyze two types of resonance circuit. Let's say it's E0 as a function of time. I can start with a sequence connection. Circuit like this. It will be P, it will be A. Input impedance ZAB. F plus omega A1 omega. It can be both inductive and capacitive, but on one particular frequency. Omega 0 equals to 1 divided by LC, it will become pure active. So current will be E divided by R, and voltage at this point is E rho divided by R, or Q E. If I have a good coil good enough, it can be 100 or 200 times higher. Equivalent quality of the contour. It will be, let's say, sum or equivalent will be wave resistance divided by R plus internal resistance of the source plus, if you want to add some load, F, or it will appear here. we can use such circuit as a band pass filter. We can use this circuit as a selective circuit. How to say, cutting some frequency band from the all frequencies. For such case, we will need to for analyze. It's good to operate with relative frequency deviation. So simple frequency deviation is nothing when shift between actual frequency and theoretical resonance frequency. But this is not you to say for each contour, for each circuit, it will be shift. So often used a relative frequency shift being omega square minus omega 0 square divided by omega square. It's a relative, how to say, relative frequency shift. And also Xi being Q omega divided by omega 0 minus omega 0 divided by omega. This parameter, common frequency shift, is very good for theoretical analysis of different circuits because it gives us it takes account of quality, so all charts will be in the same coordinate system. What I can do in case of small frequency deviations, when delta omega is much less than the resonant frequency, we can imaginary of ZAB, XAB input reactance write as double rho delta omega divided by omega 0 or rho epsilon. And input ZAB can be written as R square root 1 plus C square, which is approximately rho square decrement square plus frequency shift square. This one is useful for drawing characteristics. On small deviation. Usual current against resonance mode current use very simple 1 plus C square chart, or if you want you can use approximate square root 1 plus double quality delta omega divided by omega and take a square. It will give you a selectivity chart for good. Here it's round. This will be this parameter, and here omega 0 in It's a selectivity in frequency. I have time. For such circuit, transfer factors. Transfer factors. One moment, I'll write them. So, if you take a capacitor voltage, it will be omega. If you take output signal from the capacitor, it will be capacitor voltage divided by your EMF, really Q omega 0 divided by omega square root 1 plus C squared. The same for coil, the only difference phase shift 90 degrees. At omega being omega 0, both equals to Kc and equals to quality. Yields the same. Blah, 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 but result will be Q omega 0 divided by omega 1 plus C squared. It's a characteristic, frequency characteristic of sequence or sequent. This kind of circuit works well if you have a very low internal resistance of the source. Another circuit can be, let's say I have a source with internal resistance and we have 2C coil L1, something like this, parallel contour. A, B. Parallel contour. That's what I'm using. Input resistance of this contour ZAB, it's an input resistance, will be F1 plus omega N multiplied by F2 plus 1 divided by omegas divided by F1 plus F2 plus omega N minus 1 omega C. At a point when omega equals to omega 0, imaginary part of this will become a 0 and it will be ZAB at a resonance frequency will be rho squared divided by F or Q wave. At this moment, current can reach very high value. For good contour, 200, 300, 400 times. Such contours work very well when you have a high output resistance of your source. in case of small, so resonance current is quality non-resonance. In case you have small frequency deviations, you can use an approximate formula of rho squared divided by r plus 1 second 1 plus c. Model of input resistance is approximately rho squared divided by r and divided 1 plus c squared. And here is one moment. We will see the same characteristic on frequency as for sequential conversion. At omega 0, you see something like this. Voltage characteristic against resonance. You can use 1 divided by square root 1 plus c squared. The same thing. Transfer factors equals to say omega and equals to you can use q omega 0 divided by omega square 1 plus c squared. One can write the quality equivalent of summary divided by R1 plus R2 plus rho squared divided by internal, so a voltage of our generator. Okay, it's a blah blah blah. Yeah, it's a blah blah blah. Can I show something? I have, we thought something good about frequencies, blah blah blah. I have one instrument here. Interesting instrument. What's inside? Inside is first generator producing voltage like this. This generator acts as a for generator with variable frequency. So frequency of this generator will change up, 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 down, up, 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 down. It's called sweep generator. Up, 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 down. I have also circuit to ensure voltage stability. This This is voltage stability circuit. Output here. Test object, it will receive signal from the sweep generator. Taken back through the amplifier and absolute function and our familiar cathode ray tube. This one, output of my circuit is Y, goes to the Y channel of the scope. To the X channel of the scope goes control or guide or govern generator voltage. What kind of research figure will I get? Any idea? What will be on horizontal? Frequency. Actually, it will be a frequency deviation from some F0. From the frequency at this lower point. Yeah? Here, starting point corresponds to the generator frequency at this point. It's up, 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 up. And what on the output? Response of the tested circuit. Yeah? As a result, I will get a chart. Frequency transfer factor model. Yeah? You understand how it's happened? This instrument is called analyzed border for analyzed. Or amplitude, frequency, characteristic, analyzed. My object. It's a network of coil, capacitor, and I also have a variable resistor here. This one should go here, and this one goes here, and please stand. Oh. What do we see? You see green line? What I told? What on relative small frequency deviation we can expect and this will be have I told it? Now come here. Okay, now question. What will happen if I increase capacity? Ideas? What happens if I increase capacity? I increase capacity. I have a variable capacitor here. What will happen? On the one hand, what will happen with capacity ability to store energy? It will increase. Increases ability to store energy, increases inertia. Increases inertia. What happens with the resonance frequency of a oscillation frequency? It decreases. Look. Increase capacity, decrease capacity. Increase, decrease. But my amplitude changes. Increase, decrease. Why amplitude change? Because losses of capacitor vein change. Active area of veins change. This means losses change. What will happen if I increase resistance? More resistance, less quality. Small resistance, higher resistance. I can simulate it with my finger. I'm touching coil. I introduce active losses. So, characteristic peak goes down. In all books, you will see in all good communication books, you see a family of charts. Let's say Q5, Q something like 10, Q50, Q100. They all are drawn in relative scale. So they all come from point. M chart is Q, like something like this. And here always 1. Or, O divided by O maximum. So here always 1. They all are normalized. Real characteristic is here. I increase resistance, it goes down. I decrease resistance, it goes up. Now, question. This thing. It's a ferrite material with a good magnetic conductivity. What will happen with chart if I put it in the coil? What happened with this characteristic? Material with a good magnetic conductivity, ferrite. Ideas? Good magnetic conductivity means what? Coil will be able to store more energy. More energy in the coil means more inertia. More inertia means lower frequency. See what happens? Better magnetic conductivity, better inertia, more inertia, lower frequency. But also, you see what it characteristic also goes down. Because of magnetic losses. You need to spend some energy to let's say remagnetize this material particles. And now I have a hollow aluminium pipe. How this pipe will change characteristic? It's conductive, it's hollow, nothing, it's diamagnetic. What will happen? Ideas? We have current in coil. If there is a current, it's a magnetic field. This magnetic field induces current in this hollow pipe. Because it's short circuit, it will take energy. And we see decrease of common inertia. We see it as an inertia decrease, meaning what oscillative frequency goes up. Also, we introduce some losses. Make one trick. What happens? And magnetic material. Oh. Hey, 1 second. Magnetic and non-magnetic. In this case, frequency goes up. In this case, frequency goes down, goes up. You saw it. What conclusion can we make? Can we make any conclusion? First, second order network. This network is characterized by equation with two roots. Yeah? So it's a second order network. Second order network can have resonant frequency or being aperiodic. It depends on relation between wave resistance and active resistance. If we have small active resistance, good quality, process will, what will we will see? This nice decaying oscillation. Inside is nothing less than a sine. High resistance and process is a non-periodic or aperiodic. Point 1. Point 2. Such network has a transfer characteristic of a kind of bandpass filter. Quality of this filter depends on characteristic on network losses. Less losses, sharper characteristic. Voltage in at a resonant frequency or current in resonant frequency is much higher than somewhere else. And what else? we can note what behavior of a resonant network, this super voltage, can be explained with energy distribution on frequency. One of the way to explain it. Yeah. Second order network. Resonance at frequency periodic, non-periodic, periodic, spectrum at non-periodic, spectrum at periodic mode. This is for next time. Maybe some questions. And also named as a selective network. I have only formulas there. Yeah. I'm afraid to miss some signs. That's why I'm keeping formulas. All text is coming from my head. What? You recording remains. I think you only need to keep in mind basics. I don't know. In my business, resonant such kind of network are mostly most concern is over voltage computations and so on. If you deal with some kind of let's say inverters or frequency converters and something like this is what you will deal with. It's you have switch, coil or transformer. What will happen with my transformer? Resonant over voltage. Some techniques of fault location are based on resonant characteristic of resulting fault network, but then, in my view, not reliable. Next time I will explain what happens. Next time I will consider couplet networks. This is simple. Here we have only one contour. More complex thing is a couplet network, when we have a pair of contours. But it's for next time. What else? Yeah, it's nice to tackle someone with free energy. When you have no load, at a point of resonance, you have this nice giant voltage. You cannot take it, you cannot use it, you cannot use it as an energy source, because at the moment you try to load this contour, quality falls down and all disappears. At the end you will have a non-periodic network. But if you need band pass filter, yeah, hate this. It's nice and selective. This coil I use, it's from approximately 100-year-old receiver. It's from old radio. Well, capacitor is from some kind of transmitter. It's for high power. Coil from receiver, original. It's not reproduction. Very nice structured coil. Without cord, airtight. Such forever, it's I don't know, it's from 20s, something like this. French manufacture. Wait one moment. It's in disarray. Possible this thing heard Clemenceau speaking. Earphones. Look at this. Actually, it's a receiver. Maybe Clemenceau speak well heard on this, because it's maybe really one on ear. Air capacitor, coil. I need to spend some time here, very fine assembly, but possible. It's one resonant contour and one detecting diode. This were not original, but earphones themselves. Thomson Houston SGDE 2000 ohm. Here everything fully original, and they're working. One day I will restore it to I will restore it. One day. I have a lot of things to restore. Okay, where we are. I think it's